Dr. Judi Steinman is an adjunct professor in the Lyot University's Master of Science in Clinical Psychopharmacology and was program director from 2017 to 2022. She served as the president of APA Society of Prescribing Psychology, Division 55, in 2019, and as past president from 2020 to 2022. She co-chairs the Division 55 Training Program Director Council and is founding chair of the Division 55 Legislative and Social Action Committee. She co-authored the division's specialty petition to APA's CRSPPP, allowing clinical psychopharmacology to be recognized as a specialty. Dr. Steinman serves as a chair of the Hawaii and Florida Psychological Association's RXP committees. She is actively engaged in efforts to bring prescriptive authority for qualified psychologists in Hawaii, Florida, and across the globe. She trains graduates from all of the MSCP programs for the National PEP exam. So welcome, Dr. Steinman, and you have the floor.
It's so wonderful to see so many friends who are here today and hopefully some new friends. I actually am in Florida now. I've been here for 6 years, but spent quite a few years in Hawaii. I ran the MSCP program that was in Hawaii. And as some of you may be familiar, we've been trying to get prescriptive authority in Hawaii for 40 plus years. And we did it. We did it like 2 weeks ago. It's done. So Hawaii is officially the 9th state. And in my mind, it's really the 10th state, but that would be a whole other lecture in and of itself, because we all forget that in Indiana, there was a rule that would allow a prescribing psychologist who's allowed to prescribe in the military to practice there in Indiana. But that's a long story. That's another talk. I'm going to tell you a little story. Unlike just about everybody else that you might meet in this field of psychopharmacology, I'm a bench scientist. I grew up doing biochemical analysis of monoamines in the spinal cord and peptides and monoamines in the brain. And I was a pharmacologist. I mean, my degree was in psychology, but I was doing something that is called, or used to be called, physiological psychology. So I was always focused in on the science of psychology. And one of the things that was really interesting to me back in the day was this whole idea about what is it that hallucinogenic drugs do to the brain. And this is long before there was really a thought about having therapy-based administration of psychedelics. Over the last 10 years or so, there's been an enormous change in the field. And so I thought I'd bring some of this to you today. So I've been doing talks for about 2 years now on native ritual practices and the use of different drugs, and especially in terms of how those substances, even though they're coming from plants, have psychogenic effects, and that they potentially have interactions with medication that a person might be taking. And, with this special concern about folks in the Native American, Native Indian populations, where they may not always be forthright in talking to you about their ritual uses. So I got very interested in this field and have been talking about it for a couple of years. Somebody told me once, he's a professor at an undergraduate and graduate school in psychology, and he told me that his upcoming students really are not interested in psychopharmacology. They're really interested in psychedelics. The thought in my mind as a traditional bench scientist that people make that distinction and don't understand how psychedelics really are part of clinical psychopharmacology, and that, the training, for example, the MSCP that we offer at Alliant or the other schools around the country now, that there really should not be a distinction, but there's a younger generation that thinks of prescribed medications as somehow being disconnected from hallucinogens or psychedelics, if you will. And I will use those terms interchangeably. So I just found that kind of fascinating, the fact that they're really interested in psychopharmacology, but they don't understand that connection between the two. I feel it's our mandate as educators to bring the story to the people who are going to potentially be prescribing psychologists in the future, or therapists that are utilizing psychogenic drugs. So that's sort of my orientation in talking on this tonight. Whether you've read it in a book or seen it in a movie or had a personal experience, there are common hallucinogenic effects of many different substances, whether they come directly from plants or fungi, right? I'm a fun gal, right? From a fungus, or whether they're synthesized and created into a controlled substance. And I'm using controlled substance a little differently than the way the DEA uses it. But for right now, when you take a chemical and synthesize it and resynthesize it, and you can measure the amount of that substance, and then we can come up with prescribing suggestions and things like that. But the things that people, whether they're taking these substances recreationally or as self-medication or in a therapeutic setting of some kind, the idea that there are certain things that are common with many of our hallucinogens, okay? So really, to be a hallucinogen, the person who's taking the substance is going to experience changes in their perception of time and space. So their awareness of themselves will change. They have not just an increased sensitivity to the sensory world, but they'll have something called synesthesia, which blends our different senses. And I will talk about that a little bit in terms of LSD as a super agonist, which is not a term that everybody uses, but I'm pretty convinced that of all of our substances that we'll talk about today, that there is a very unique property about LSD that, and I'll give you the punchline now, that it is not only affecting 5-HT2 receptors, serotonin 2 receptors, but it's also modifying glutaminergic receptors. And so glutamine, of course, is an amino acid or it's amino acid derived, I should say, neurotransmitter. It's just a simple amino acid, and it has its own neurons that it gets released from. It has its own receptors, and there's a number of different kinds of receptors that glutamate binds to. But it's something unique that really all of our hallucinogens, especially the ones that have indole amines, I'll talk to you about what that means in a minute, that they have this additional ability to form a complex with the serotonin receptor and the glutaminergic receptor. And that is what is most likely responsible for at least synesthesia and paresthesia, where you feel what you see, you hear what you are tasting, things like that, that really bend our understanding of what sensations are to the body and to the mind. Okay, but these are the general things that people will report experiencing with hallucinogens. And this is a list. I just like the colors in it, but it does have a pretty thorough list here. I am not going to talk about all of these substances tonight, but we have certain ones that bind very specifically to serotonergic receptors. That's going to be LSD. We have psilocybin. Psilocybin is from a mushroom that is going to have hallucinations that are more similar to LSD than any of the other hallucinogens. With mescaline, that kind of has its own mechanism of action, and chemically it does differ substantially from the LSD psilocybin chemical structure. PCP, ketamine, we have lecturers here who speak about ketamine. I'm not an expert like they are, so I'm going to leave ketamine to the side tonight. But as you can see, there is a long list of both chemicals like marinol and sesamet. I actually worked on marinol and emesis years ago, years and many decades ago, and then we have the experiences as well. So these are just to remind us, those of us who have never had the experience or haven't had it in a long time. I like these, there's a couple of slides that really I connected with as a research scientist that talk about this theory of being a superagonist and how that goes about working. Now, serotonin, one of our monoamine neurotransmitters, is going to bind to its own receptors. Now, as far as I know, there's over 7 different kinds of serotonin receptors, okay? But they're all specific. They have binding sites that are specific. So when serotonin's floating around the synapse, it will bind in some way. It might be in this direction, it might be in this direction, but it will bind and connect with the receptor. And then the receptor will do what it normally does, which is to eventually trigger an action potential and propagate signals in the nervous system. This idea, though, that when we have hallucinogens on board, that we're also affecting the glutaminergic neurons, the excitatory amino acid neurotransmitter system that is going to have effects on our perception, including of sensory. And the idea that we flood our nervous system with serotonin and serotonin-like substances, with the addition of disrupting or changing how glutamate is going to bind to its receptor. So that's kind of my take-home message right up front. Now, since I do teach biochemistry, I have to have some chemistry in here somewhere. And look at this. This is the indole ring of serotonin. We have an aromatic ring. These are all carbons at each of the corners here. And then we have this 5-cornered structure that makes it an indole, and it has a nitrogen instead of a carbon. If you don't see anything written, it's carbon, right? So here we have carbon, 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 nitrogen. And nitrogen, when combined with hydrogen, is a very polar substance. So it is going to change the way that chemical is going to interact with receptor binding site. And then, yes, we have an amine group, nitrogen containing hydrogen, a couple of hydrogens. And so again, we have 2 polar groups in serotonin in and of itself. Here's psilocybin. And psilocybin is so interesting because, yes, it has that indole ring structure combined with aromatic in this ring. And then it has the nitrogen with open bonds, and that's usually at physiological pH. And so we have this NH bond, but we also have the ability to bind to other sites in addition to the sites where nitrogen might be binding, but it has additional possibilities on it. But the really cool thing about psilocybin is this phosphate group here with oxygen, right? And phosphate, when you strike a match, that takes energy, right? And so psilocybin brings its own energy to the party, if you will. That will eventually get released. We'll talk about metabolism in a little bit, but we are providing energy to the brain when psilocybin is taken. So the things I've read is that differences between LSD and psilocybin are that the hallucinations that people experience on LSD is more angular. So it's like triangles and squares, and whether they're talking about the visual trails that are imposed on their occipital lobe, or just looking at objects, that things are angular, and that when people take psilocybin, all the edges are smooth. So their hallucinations are circles and oval and shapes that have smooth edges. And I don't know if anybody has ever looked at that, but it's an interesting observation. I don't know how far I can take that, but there are distinctions between how a person's perception changes when they're taking psilocybin versus LSD. So here's the LSD. Now, it's a little hard to tell, but we actually have an indole ring here attached. These are all aromatic rings. LSD is almost like some of our tricyclic antidepressants, okay? It's got multiple ring structures in it, and this does make it similar to the indole structure that we have with psilocybin as well as serotonin. But as you can see here, in addition to this would be your amine, your primary amine group. But we also have a double bonded oxygen, so that's an ester group probably. And then we have additional methyl groups on the end. So it is different, and this actually shows you this would be another way of expressing the chemical structure. And this would be serotonin. And you see those similarities here for LSD, but then it goes on and it has more expansion. And so the idea, this super agonist idea, might involve this additional component, and we'll talk about binding properties later on. This is just to point out to you that the 5-HT2A R receptor has great affinity for just about all of our LSD and psilocybin, and of course serotonin, right? It might be having multiple effects. So it might be having hallucinogenic effects where you're actually seeing things or hearing things that are different. Psychedelic effect, although I use those terms interchangeably, the more rigid definition would be the psychological effects of taking hallucinogens. There are non-hallucinogenic analogs, so other drugs that will bind to the 5-HT2AR receptor. Think about some of your atypical antipsychotics. They do have 2A, 2AC binding sites, so various ones. And then there's this concept of antidepressant effect. And, this is what we're trying to study in studies to see if our hallucinogenic drugs can fall under a different schedule, right, for under the DEA, because it does have clinical effects. For those of you who aren't familiar, Schedule 1, which is where our hallucinogens lie pretty much, means that the drug has no useful medical application and very highly prone to addiction. So that's how we get classified as a Schedule 1 drug. And so right now, our hallucinogens as a broad category do fall under that schedule. But if we're able to really demonstrate antidepressant effects, then it can move over into probably Schedule 2. But it's coming. It's coming down the pike. So I'm not going to test anybody on all the structures of classical serotonergic psychedelics, but I did want to point out, in addition to LSD down here, and here's psilocybin, and there's our beautiful indole amine structure, we do have MDMA that is thought to primarily bind to glutamate, but has our indole structure. Now, it has a slightly different chain off of it, but it does have that indole structure. This is ibogaine, which our current president has recently expressed interest in seeing more research done on this drug. And it does, in fact, have the serotonergic component to it. This is DMT. This is the LSD, right? And so here's our indole group. This is MDMA. And so it doesn't quite have an indole group to it, but it does have another 5-cornered structure. And then it has its nitrogen amine group sticking out. And these amine groups are very important for binding to receptors. Here's ketamine. Ketamine is different, but it does have that amine group sticking out. And it does have the potential. It's a little hard to see on 2 dimensions, but in 3 dimensions, you would be able to see that there would be potential for additional bonds. So it's kind of like taking the bottom out of this ring here. And then, of course, here's serotonin. Now, mescaline, I kind of left on its own for a little bit because it certainly has its own hallucinogenic properties and psychedelic properties, but it is different from these indole amine structures. This is an aromatic ring. It's just drawn a little differently. It's kind of like Spanish and English and French. We have different languages, and in chemistry, there's different ways to draw things. So it has a lot of methyl groups on it. Here's 3 methyl groups. Has an ether bond. It has a primary amine, but no indole ring. And so some of the differences between mescaline and our other psychedelics might be because it is lacking that indole ring, but you will experience the profound psychogenic or psychedelic effects of mescaline. Which part is really essential for each of those components of the overall effect of taking hallucinogens? That's not clear now. But it might be that if you added an indole ring onto here, that you might have the ultimate or penultimate hallucinogen there. I find mescaline very interesting because it is natural, first of all, and that is something that the people who think there's a difference between psychedelics and hallucinogens and psychopharmacology, that they are a little off target there, because natural products are really the source of most of our medications, not just psychogenic medications. Usually it's the dose. The dose is the poison. And if there are too many side effects of a medication, then a person's not going to take it. But interestingly, people will take mescaline, they will take psilocybin, even though they have pretty profound adverse reactions, vomiting, nausea, but people seem more connected with taking something derived from a plant. And this is the structure circling. I like this. But mescaline does have a unique structure in and of itself. And you can tell, I figured since I'm talking about hallucinogens, I should have lots of things flashing and with color. But this is a very interesting study. This is out of Washington University. And this is a heat map of brain activity that they looked at before treatment. And you can see that most of the colors are blue and green. This is during a trip on psilocybin. And you can see, and it's flashing in and out here, but you can see that there are areas of the brain that do experience profound changes in activity patterns. And then long term, if you stop taking it, but after a while, the patterns in the brain do return to pre-psilocybin levels. And so it's really kind of interesting in using technology now like this to be able to illustrate that when people take hallucinogens and they go through all these different experiences, right? Feelings, sensory changes, thoughts of profound significance to that person, that they are all related and activated throughout the brain, right? Making it as attractive in some ways as ketamine, if we can control the administration of it, for working on depression and PTSD. So here's our psilocybin mushrooms. When I lived in Hawaii, I had a cow pasture, and psilocybin mushrooms were popping up all over the place. And I don't know if the cows were aware of that, but they grow pretty commonly in agricultural areas. And also in the woods, you can find psilocybin mushrooms. But here's the chemistry of what happens with psilocybin. What's interesting is, so here's our molecule. And so psilocybin is going to go through a metabolic change that converts it to psilocin, which is a active metabolite, right? So psilocybin can be active and then it converts to psilocin. And it's an active metabolite as well. So in some ways, you can think of psilocybin as the parent drug. And there are additional metabolites that break off. Here in this little box here, it says Fe4. Now that's referring to iron. We have this whole group of enzymes. We usually just talk about them in the liver, but they're actually ubiquitous around the body. And they're called CYP enzymes for cytochrome P450. And so the thing that makes CYP enzymes what they are is the presence of heme. And in the center of heme is iron. So as it turns out, there are CYP enzymes involved in the metabolic path to create psilocin. And then what you can see here is that we have multiple additional metabolites that come out of the psilocin that are phase 2 metabolism. So we have phase 1, which is CYP enzymes. Phase 2 metabolism is when we're trying to make a compound less lipophilic so that it can get eliminated through the urine. Only hydrophilic substances can pass from the bloodstream into the tubules of the kidney and get passed out through the urine. So when we have a couple of different phase 2 enzymes involved, that means that we're trying to make the psilocin more hydrophilic. And you can also see we have aldehydes, we have MAO, monoamine oxidase. And then one interesting thing is that psilocin has a very active metabolite, and that is serotonin. So in addition to the parts of psilocybin that mimic serotonin at the binding site, we also have a recycling of the portion of psilocybin that will create serotonin. Okay, now I know this is small, but this is just to show you that we have multiple chemical classes that fall under this hallucinogen category. Tryptamine for LSD, tryptamine for psilocybin, phenylethylamine for MDMA. Mescaline is also in that phenylethylamine group. And then here's DMT with tryptamine as well. Tryptamine is part of the pathway for plants to make serotonin. We, mammals, make serotonin from tryptophan, right? So I just wanted to make sure we were clear on it. These products that are up here are derived from tryptamine, following the pathway that plants use for synthesizing or mimicking serotonin. This slide I've included just to make sure I've satisfied my personal goal of making chemistry a little less scary, maybe. And I know it's very small, so you'll have to blow it up. But I did give you the link to the article that this comes from. And it has compounds that act at serotonin binding sites. It also has compounds that act like amphetamine. Those that fall into that class of phenylethylamine usually are doing what, at least part of it, what amphetamines do. Now, the interesting thing, when we think of amphetamines and ADHD, we think about the amphetamine spilling out norepinephrine and dopamine, but they also spill out serotonin. But we just don't really talk about that when we talk about ADHD treatments. So is there a hallucinogenic property to our drugs that act like amphetamines? And for those of you who don't know, amphetamines are going to cause vesicles within the neurons to spill out their content. And what happens is, after a while, you've depleted the energy in that neuron to make more vesicles. And so when somebody is using amphetamines to get high and they have a crash, it's that crash is because they have depleted their neurons of neurotransmitter. And so is it the serotonergic component that we don't focus on when we're thinking of ADHD, but is it possible that there are potential drugs that can be developed that would help us with ADHD and enhance the psychic part of how these drugs work? It's an interesting idea. I'm not really sure yet. Anyway, so you can classify your hallucinogens into these various categories. This idea that activation of the 5-HT2A receptor enhances glutamate excitation in certain layers of the prefrontal cortex, and then it gets released going from the way station of the midbrain or forebrain, from the thalamus up to the cortex. So what is getting filtered is essentially one of the roles that glutamate plays. Glutamate and GABA are always balancing each other out. But what happens, or one of the theories, is that we affect the release of glutamate from glutaminergic neurons, and we change the activity of the receptors, because when we bind to the serotonin receptor, if this is our glutamate receptor normally, and this would be, your ion channel, if LSD or serotonin are binding, and we can make that channel open wider, that's a conformational change in the receptor that we might be seeing. And we all know that glutaminergic neurons are very involved in their interneurons and very involved in cognitive processing. Is it that LSD and psilocybin are modifying glutaminergic receptors in the prefrontal cortex? Is that a possibility? It certainly is. But there's this idea that we're either changing the receptor structure to enhance glutaminergic activity, or we're changing the way that glutamine is getting released from the neuron. pKa's are generally pretty high for our hallucinogens in general. I pulled these from various sources, but the idea that our pKa, our acid dissociation constant, is on the basic side means that these drugs will go through pharmacokinetics, absorption in particular, similarly to how our SSRIs, many of our psychotropic drugs work, because they all start out with a high pKa so that they will get passed from the stomach into the intestine, where they can get absorbed at a different rate than if they just pass right through the stomach lining. So they're all probably going to act more like a number of our psychotropic meds, which is good, because the goal is to get our hallucinogens up to the brain to have their effects. This is looking at nicotinic receptors and glutaminergic receptors. We're not talking about nicotine today, although, when we talk about ritual practices, tobacco is a very important part of Native American practices. And so it may be that when used in ritual ways, that we're also affecting our glutamine receptors with nicotine. But I like this image because it does give you that idea of ways that you can modify the glutaminergic receptor by modifying other receptors. This is very important to the concept that I'm talking about. And so what happens is the binding to 5-HT2A receptors is going to change certain glutamate receptors, not all of them, but it's going to change the mGlu2 receptor. And it forms a complex. So this would be LSD, and this would be LSD, and its effects on the glutaminergic receptor. And this was an animal model that they used, but it's when this component, the changing of the glutaminergic receptor, happens, that these mice show, certain behaviors associated with taking LSD. So it does seem that at least this property of head movement is sensitive to that change in the glutamate receptor. I love crystallography, so this is literally supposed to represent each of our transmembrane domains that our receptors make up. This would be LSD binding to this is a 2B receptor, but the mechanism is thought to be similar. So this is our LSD, it's binding here, and then the ribbons will allow your ions to come inside. They did identify different parts of LSD that activate the receptors differently, so might be responsible for additional effects. The other thing I want to talk about are CYP enzymes, and this is very important because your patients may be taking hallucinogens in addition to medications that you prescribe, or they're getting prescribed by somebody else. But you should be aware of the fact that if they are taking an SSRI or an SNRI, and they're taking psilocybin or LSD, they may create problems with the availability of receptors and binding sites on the enzymes for the drug that you're prescribing. So LSD involves 1A2, 2C9, and 3A4 CYP enzymes, okay, for its metabolism. And also 2D6 and 3A4 for another pathway. And so these are enzymes that just about all of your psychotropic drugs depend on for their proper metabolism. And so if they're taking LSD along with psychotropic meds that you've prescribed, you want to make sure that either they've taken into account the half-lives of the LSD versus the medication they're taking. If they're taking fluoxetine, for example, the very long half-life, they may end up with something called serotonin syndrome. We all know basically that's a bad thing. And so this is just kind of to illustrate for psilocybin that we also include the CYP enzymes 2D6 and 3A4. They just call it CYP P450 here. But it is this modification through the CYP enzyme that might create a drug-drug interaction in your patient. Ketamine is fully legal to prescribe in all 50 states. I don't know that there are prescribing psychologists who prescribe ketamine, maybe in New Mexico, but for the most part, it's a physician or psychiatrist who's a physician plus. Psilocybin is legal in certain states, and all other psychedelics still remain on our Schedule 1 list. And this is just a little bit more detail about that. These are the new guidelines that came out last week, and they're still in the process. This review process within the FDA started, I think, in 2024 for consideration of clinical studies that can be done with hallucinogens. Designing the study itself is a little challenging because it's hard to use traditional placebos, and there really are not any DEA drugs on any of the other schedules that you could compare directly, use as a positive control, if you will. So we do have to be a little bit more creative in the way we design these studies to do the comparisons. Sometimes they'll do pre and post. We do have crossover studies that can be done. There are approaches that can be taken, but it is a specific challenge to hallucinogenic drugs. And if you look at what the marijuana industry has done in terms of creating much more uniform definitions and dosing and things like that, it's really remarkable to me, and make it clear that with the right thinking that goes into this process, that we can come up with appropriate study designs that would be used for evaluating psychedelics. So this is just more from the guidelines that they're creating. This link will take you to the document itself. This link takes you to the preamble about this guidance document that's being created. The net effect is probably going to be moving at least the natural psychedelics to Schedule 2. All right. Unfortunately, I am not going to have time to go through all my plans. These are substances that are used in ritual practices by Native American, Native Indian cultures. I just wanted to point out that, for the use of tobacco, for example, nicotine is considered a inducer of the 3A4 enzyme, in addition to other components of tobacco smoke. But nicotine itself is an inducer of 3A4, the CYP enzyme. And so what that means is you're going to metabolize more quickly. So if you're taking a given dose of a medication, the effect will run out sooner, essentially. And then peyote, mescaline, I just want to point out that it does have some binding properties at serotonin receptors, but you saw the structure. It's really not like an indole amine, so it's not going to work quite as efficiently at those receptors. For peyote, this is some of the pharmacology and adverse reactions to expect. And, it's interesting to me, though, that people are willing to take peyote and go through these adverse effects, knowingly will experience those to reach the place where they can have that psychedelic experience. So in terms of harm for all of these drugs, you can see that heroin, methamphetamine are very high, and our hallucinogens, for the most part, are much lower on the scale of overall harm. For those of you who are not in the prescribing psychology field, I just wanted to point out that we do have our 9 states now, and Vermont and Hawaii. This is the first year we have added 2 states in 1 year. So we are moving forward, and now we can officially be from sea to shining sea. We have prescriptive authority. And Division 55, please consider joining if you are not already a member. We just grew to the highest number this year. I think it's 1,070, 1,080 people. So we are a growing field, and please be part of it. Any questions? All right. So how 5-HT2A receptor agonists alter cortical network connectivity? It is a great question. So that image that I showed you with the flashing energy levels on the brain, connectivity between the cortex, the thalamus, and the striatum, which is so interesting in and of itself, is essential for developing resilience, personal resilience. And there are studies that have been done, mostly out of Alabama that I've seen, but there might be some other studies. And I can send you these references if you email me. And they have shown that people with substance use disorders have unusually low levels of connectivity, okay, in that triangle pathway. And that as people go through abstinence and develop skills for staying off of medications, that the activity in those pathways increases. So it's not just a question of something binding to a receptor. It is this strengthening of the firing between those regions that contributes to our ability to utilize therapy for treating anxiety and depression. And so those studies where we're seeing this increase in activity in the prefrontal cortex, that in relation to the hallucinogens is part of that pathway. That activation of that pathway then leads to excitation levels throughout the brain. I hope that makes sense.
Yeah, you're just getting a lot of positive feedback, Dr. Steinman. What an amazing presentation. Thank you so much. And Dr. Kapalka, always thank you for attending too.
Thank you, Dr. Steinman. It is always great to hear your presentations. And those of you in the audience who would like to learn more or who would like to learn more about psychopharmacology and hear Dr. Steinman speak about this and many other topics. We are enrolling students to start in our fall cohort, which starts August 24th. So we would love to hear from you.
And if anybody's interested in prescribing in Hawaii, please let me know, because we have this 3-year pilot study where we've started working on it already.
Congratulations, Dr. Steinman, and the whole Hawaiian team. This has been many years in the making, as many of us know. So hearty congratulations. And yes, we would love to see many prescribers come to Hawaii.
Thank you, Dr. Steinman and Dr. Kopalka. Again, everyone, thank you so much for attending. These are always amazing presentations.
Mahalo.